machine learning for Incode. He is a professional with extended and long-standing career. He has been working for well-known companies like Huawei or Bosch, and today he is going to talk us about the face verification and the face identification things that they work in Incode. So thank you very much, Efim, for joining, and the stage is yours.
Thank you, Iago. Does it work? Does the mic work?
No, now it's okay, but it's just for the transmission.
All right. Okay. Okay. Yeah, let me know if you cannot hear me. All right. Yeah, welcome everyone, and thanks for having me here. It's a great pleasure to talk at Madrid ML Meetup. I moved to Madrid like 1.5 years ago, and for me it's a big honor to present here in front of you. So to move this, okay, I just do it. So today I'll be talking about face liveness and deepfake detection, but more specifically about using recent advances in AI to significantly improve performance of these models. So just a couple of words about myself before we start. So, so yeah, I was born in Moldova. I spent most of my life in Moscow, and I studied in top schools there, and I did my master's thesis at MIT. And yeah, as Iago mentioned, I worked in research centers at Huawei and Bosch, and at a couple of startups. Then I moved to Madrid, and here I remotely work for Incode. We are identity verification unicorn based in US, and yeah, today we will be talking about that. So I'm sure all of you have experienced remote identity verification. So when you want to create a new bank account or another service, and you need to verify your identity, you use your passport or ID and then your face, so that you can match the face, your real face, with the face on the document and make sure that it's really you. And obviously there are two things that you care about in this kind of systems. So one thing is that it's very convenient. It doesn't take a lot of time and a lot of efforts. But another important consideration is security. So you want to make sure that no one is using your face to, do some illegal activities to create some fake account and get some loans under your name or whatever. So you want it to be both secure and user friendly. So how do you get all that? So that's, here we will see an example of how a person tries to spoof the system. So you see that's some identity verification software, and this guy uses Mike Tyson's mask and tries to breach him basically, and he was successfully able to do that. So he's like the mask, the 2D mask of Mike Tyson was accepted, which is like obviously not the performance that we expect, right? And that's what we call a physical attack. So there are, it can be like like this one mask, or it can be a photo, or it can be a video shown on a screen. So everything which involves some physical object, we call it like a physical attack. But there are also digital attacks, and obviously you all know about deepfakes. So this guy looks very convincing, but actually you guess that, yeah, it's a deepfake. So that's the actor driving this deepfake. Actually, actually it also uses the same voice as the target person. So yeah, we at Incode try to deal with all this stuff, and the landscape of attacks is huge. So as I mentioned, for physical attacks you have a lot of different variations, but even for digital attacks as well, you have like different kinds of deepfakes. You have face swaps, when someone uses somebody else's face, or face morph, when two faces are being mixed. And yeah, there are different. There is like for example, synthetic faces, when you just like, you all heard about Midjourney, Stable Diffusion, and so on. Like some models that just generate new synthetic faces that were not existing before. So all these attacks it's a huge landscape, and the goal is to be able to detect all of them. Before we move on, do you think that any of these three are or is a spoof attack? Who thinks is the first image on the right? Okay, one person. Who thinks it's in the middle? Okay, okay, more people. And who thinks it's the third one? Okay, majority votes for this one, but we had votes for each of them. So let's see in the future how it works in the end. So, but yeah, like all of them look kind of realistic. So yeah, we don't know. We don't know. So in general, there is this huge dilemma that in our industry, like in industry of face liveness or face anti-spoofing, is passive versus active liveness. So let me explain the difference. And like passive liveness, it's the experience that you get here. So you see, it's just like making a selfie. Very simple, very quick, and it doesn't require any special efforts from your side. And yeah, that's obviously pro. But on the other hand, like it has less input data, so it just has basically a selfie, and that might be a little worrying that maybe there is not enough information about the scene, about like the person, and maybe it's a little insecure, and also because of that you kind of are forced to use more basic algorithms in some way. So that's passive liveness. I mean, you can see our logo, so we are proponents of passive liveness, but we will talk about that. And obviously, I think all of you went through this like really unfriendly experience when you have to rotate your face, or you have to rotate your phone, or you need to move it further or closer, and then you do it and you don't know if you did it right, and then the next day you get an email, you know what, can you please repeat it? And yeah, obviously that's not something convenient, and usually because of that also the algorithms are slower, and you usually you don't want to do it often, or you don't want to do it like in public places, for example. It's not really convenient. But on the other hand, it uses more data about the scene. It knows more what's happening, and because of that, it might be more secure. On the downside, again, like in addition to what I already said, is that it is actually kind of impossible to benchmark active liveness solutions. So imagine if you have like a solution that works just based on a single selfie, or based on a single video of a person just looking in front of the camera without doing anything. You can compare different algorithms, how they work on this kind of data, right? But imagine when you have a system that says, okay, you need to actually do some action, and this action might be different from one time to another, and between different active liveness providers, they ask for different actions because it's very like it's patented. All of them they use patents to secure all of their like technologies. So you cannot even compare several active liveness solutions, and also you cannot compare them to passive liveness solutions. So it's kind of doesn't seem to be the best solution in a long term. So the question now is how to merge these two worlds. Let's brag a little bit about Incode. So these two plots show our improvement through time in detecting different types of attacks. So on the left hand side, it's a physical attack detection. So on the vertical axis, it's basically the error rate, like false rejection rate. That means that you reject a valid selfie. And on the horizontal axis is false acceptance rate. That means that you accept wrongfully like an attack. So obviously you want to get to 0-0, right? To get 0 errors in both directions. So that's how we went from early 2023. It was like, I mean, around 10% false false rejection rate. Yeah, don't blame us. But now it's like less than 1%, and also like false acceptance rate is also like one order of magnitude less. This is on some particular data set that we collected. It's very much resembles data from production. That's one thing. Another thing is deepfake detection. So for the first time, like history, we were able to outperform humans in detecting deepfakes. So this blue circle represents the 5 people labeling images, and the majority voting is like represents the final label for each sample. And you can see that our algorithms, which are 2 crosses in the bottom, in the left corner, like 1 order of magnitude better than even 5 people working together really hard to detect all these spoofs. So that looks fantastic, and we were obviously very happy when we got these results. But there is always a but, right? So for example, yeah, this is one of our latest models for detecting physical attacks. On 2 data sets, we call it hard spoofs and bounty program, doesn't matter, it's like some complicated spoof attacks data sets. We still have around 4% false acceptance rate, which is like, I mean, you don't want to have these. Imagine that one of these is about stealing $1 million or whatever. So you don't want to have this high false acceptance rate, even on the hardest data set. Yeah, we kind of created these data sets so that they are hard, and so that they are challenging for us, so that we see where we can improve. But anyway, we want 0. That's our goal. So, and also with deepfakes, so there is one data set that is similar to production attacks, and here we have around 2% false acceptance rate, and another data set with deepfakes that are generated through online tools, also around 2%. So it's good, but it's not great. So our goal is like, how can we improve? What is the direction that can help us to get a completely different level of performance? So I mean, you all know you are here because you all know that AI is advancing like exponentially, and like all this like I like to think about it as like when vision transformers appeared like 4 years ago, and with them it was we were able to detect not only like some statistical cues about pixels and their neighbors, but also some semantics about the scene, and that dramatically improved the whole computer vision landscape. And then we have vision language models, which combine embeddings from language and embeddings from vision in the same space, and then you have this much richer representation of the world or of the input data that can even better, like you can get even better results with that. And the next step is multimodal models. So that's just one of the examples of a language bind. And here you have multiple modalities. Like you have vision modality, you have language modality, depth, infrared, and many other modalities that they all together can help you to understand the world better from different perspectives, basically. And as one of the examples of foundational model is depth foundational model that is actually like 0-shot depth prediction. So given all that, like, is the dilemma that we were talking before, like security versus user friendliness, still applicable? Can we change it? So my hypothesis is that using like AI, these most advanced algorithms that I mentioned on the previous slide, plus the proper data. I mean, by proper data, I mean good training data with hard samples and so on, and also different modalities in the input for the algorithm to make a decision. plus keeping passive experience, we can get ultimate security while having the best user friendliness possible. That's my hypothesis, and I have 2 experiments to show you today that I hope prove this to be working. To visualize my idea, let's look at the following. So that's the basic passive liveness setup. You just have one RGB photo. So you see like one modality, which is RGB, in one moment of time, t0, right? So it's just one data point. And the vision that we have is to go from here to this exponentially much more data. So you basically go from a dot to a 2-dimensional space, and with this exponentially more data, effectively you get the presence effect. Like you basically, your ideal goal is to have effect that you have the second person that you trust that stays like with this person who is trying to log in, you know. So that's what we try to achieve. So to have multiple modalities besides RGB, also to have depth, motion, and other possible modalities, and to have this all in video. Then you have much more data, and with much more data you get much more knowledge about the scene. All right, so that was the introduction, and now let's have the interesting stuff. So experiment number 1, it's depth enhanced face liveness. For this experiment, we consider publicly available model language bind. I already showed this schema before. So what it does, it takes multiple input modalities, and for each of them it has a corresponding encoder that works for this particular input type, and then it maps this input to a joint embedding space, which is linked to language embeddings. So basically, if you have a video, an infrared image, and a depth map of some scene, theoretically you get the same embeddings like here. They are basically the same, but in real life they are a little bit different, and they help each other. So because they show the world from different sides, and also the measurement systems that you have, they are not ideal. They have some let's say physical errors and physical imperfection, and because of that you basically see the world, you see the scene from different perspectives. And when you have all of them together, you get more information about what's happening. So that's how language bind works. So that's a publicly available model. We don't claim anything here. And the experiment setup is the following. So let's imagine, first we just imagine that we have not only the RGB input, but we also have depth. We imagine that. So for the image, for the RGB input, we do some preprocessing, and then we feed it into the encoder, the image encoder of the language bind model. We calculate embeddings. So we do the same for depth. We calculate embeddings for depth. Then we do some, for example, we concatenate these two different embeddings, and then we build a simple classifier, like machine learning classifier, that gets these embeddings as input and outputs is it a spoof or not, just a binary classifier. For training this classifier, we collected 10,000 spoof attacks of 2D nature. Like that means that they are flat, and we intentionally did that because, I mean, obviously, if you want to use depth as something that helps you, you want to get some additional knowledge. So for example, if you have a mask, you know that it's flat. If you have a screen, you know that it's flat. Okay, not all screens are flat, but yeah, so most of them are flat. So you can use the depth information to help you, you know. So if for example, there is another type of attack, 3D masks. It's like in Mission Impossible when they wear like fully realistic 3D masks. In real life, they are not that realistic, but anyway, so depth won't help with this kind of attacks, obviously, because this mask would just repeat the shape of a human head, so it doesn't make any it doesn't add any value. But with 2D attacks, that obviously can help. So we collected 10,000 spoofs, split in train, validation, and test as usual. And important note, for depth source we used iPhone true depth camera. So probably most of you know that, like, you can log in with iPhone with a face because they have this true depth camera. So otherwise they wouldn't allow to do this kind of stuff. So apparently it's possible to retrieve this depth map from iPhones. There is API that you can use. And so this guy is holding a 2D mask, which is flat. I mean, unfortunately on this screen it's hard to see, but yeah, here, like, this depth is actually showing that it's flat. And this is a normal selfie. And I mean, it's all black, but actually, like, when you convert it to matrix, you see that there is a difference. So maybe I should have visualized it in a better way, but the difference is visible. But what's important to note is that this is not a perfect depth measurement system, because you see, like, there is a lot of noise, and in general, like, it's just a very simple device. It's not perfect. But so what we have these images, we have this depth, and we have language bind. Let's have a look at the data. Let's have a look at the embeddings that language bind produces based on this input. When we saw this visualization for the first time, we were, like, so much impressed, because look here, blue dots represent valid selfies, and the rest are different types of attacks. And you see, like, such a perfect differentiation between these two classes, even though language bind was never trained obviously on these kind of attacks. It was just trained, I mean, to work on generic data, and most of it was even synthetic, so it was not even related to, like, real life attacks. And so that was first thing that we were very much impressed about. The second thing is that even between different types of attacks, you can see some kind of differentiation. For example, red dots, these are 2D masks, and orange dots are replay attacks. Replay means that it is shown on the screen, and you can still see the difference, which is very, very interesting. Obviously, when we saw that, we were very optimistic about the results that we are going to get with that. So this guy, you remember him, right? So you were right. It's a spoof attack. It's a photo shown on a screen. It's a very realistic one. Like, you don't see any cues that would show. Like, usually you have, for example, some light reflection or some border of the screen or moire effect. You know, like, sometimes when you take photo of a screen, you see this pattern. So it's like moire pattern. And you see here nothing, but you see that's the depth map. Like, it's flat, completely flat. And obviously, like, if you think about it, if you have more or less, like, adequate embeddings that work with depth, it should, like, differentiate this and a real human, right? Like, you expect that to happen. And these are the results that we obtained. So on this plot, you see, like, the red curve representing I mean, we call it APCR, BPCR curve, but actually it's kind of ROC curve, but a little bit inverted. So the goal is to get as close to 0 as possible as before. So and the green one is the RGB baseline. So it uses just RGB input. And you see, like, tens times better, like 1 or 2 orders of magnitude better. And if you fix for particular severity level, I mean, we usually fix particular thresholds to have different options for different clients, depending on, you know, how critical it is for them to have false acceptance rate or false rejection rate, whatever. And, like, for different severity levels, we see 10 to 30 times improvement, which is, like, wow, like, the effect was great. And like if you go back and you think, okay, what was the investment here? The investment here was just to take the language bind that was, I mean, publicly available, and then you just collect some data. You use already, yeah, and that's it. I mean, and you train a simple classifier and you get this improvement. So that was wonderful. Obviously, we don't use that in production, but that's if such a simple thing gives you huge improvement. I mean, and we worked on that model on this RGB baseline. It's not a baseline. It's actually a very good model that we've been developing for years. And I mean, we were a little bit sad as well. So it's mixed feelings. You might say, okay, that's great, but that's iPhones. They have depth map. What about other devices that don't have these kind of devices? And my hypothesis, this has not been fully tested yet, but I'm just sharing with you some ideas. We are discussing here at ML Meetup. We are here to talk. So the idea is to use some kind of monocular depth estimation to try to get that. So, for example, there is depth anything v2. I saw that you had a talk about segment anything v2. Yeah, they were inspired by that name, but there is no connection between them. So the idea is that, I mean, in general, often monocular depth estimation models, they have usually like an encoder and a decoder. So encoder takes as input the RGB image, and decoder produces the depth map. That's usually how it works. And here they use Dino V2 encoder, which is a like famous foundational model, a famous transformer. And then decoder is Midas, which is very famous in the world of depth maps predictions and so on. The funny thing and the interesting thing is that, so when you train Dino, probably you know that there is like a teacher and a student framework. So teacher was trained only on synthetic data. So they had some RGB images, and the corresponding depth was purely synthetic. And then for unlabeled real images, it was used to create pseudo depth maps, like from the teacher. And then the student was trained on these real images with pseudo labels. That's how it works, like basically. So let's look how it works on our domain. That's a normal selfie, and you see, very accurate, very good depth map, but you would expect that. What about spoof attack? So that's a printed photo, obviously, and it's a pretty good result, right? Like it sees that it's a face, but it doesn't fall. It doesn't fall into it. So it still shows that, okay, this is flat. It's okay. And they're like, okay, good. And what's next? Okay, you remember this guy, yes? So unfortunately, it thinks that it's a real person. And that was kind of predictable somehow. So what are some of the ideas that could be used to overcome this? I mean, one of the ideas is to so given that this model was trained on synthetic data, obviously it is kind of forced to predict depth even if it doesn't exist, right? So I mean, any synthetic image doesn't have depth. It's technically it's zero. So it is trained in the way of predicting depth, of imagining depth based on the content. So if you force it to see the difference between imagination and real life, I think it's possible to fine tune it. That's one idea. Another idea is to have this depth prediction, but to have like two losses. One is corresponding to depth prediction, another one is corresponding to face liveness classification, for example. I mean, there is a third idea which is like really simple and probably it should work, but we haven't tested it yet. It's just not use the depth prediction if it predicts that it's a human. So basically you have a language bind as a classifier, and then if you see that based on this depth map it says that it's a human, you just don't use it. You just use this normal RGB. I mean, that's like a hotfix, but that can work. So that's the idea about using depth. So you see like huge improvement, but it's limited to devices with depth prediction, and there are some ideas how to overcome that. Let's talk about next experiment. So we talked about going into modalities. Now let's go into video space. So all right, so video-based face liveness. Yeah, so as I mentioned, we grab this horizontal line corresponding to RGB, but in the video space. So yeah, we are capable of recording videos when people go through our onboarding. So we can take multiple frames from these videos. Then we compute embeddings of using some backbones of our developed models that we worked on before, and then we can do different pre-processing for that. But I mean, we can concatenate them, we can average them, we can do some really simple stuff. So let's start with just averaging. Then we average these embeddings. We train a classifier, and then optionally we can take a maximum of the prediction between the single frame model and the video model. So that's a simple pipeline that we just want to test if there is any difference between single frame model and video model. And here are the results. So basically, these are physical test data, physical spoof attacks. And you see that with the video model, we were able to get 0 false acceptance rate. With the baseline model, it was quite close to 0, to be honest, but it's very nice to have 0. So you see that like huge improvement, and then the interesting part is that you not only get improvement in one direction, but you also get a better false rejection rate. It also reduces, and it reduced like around 1.5 times. And when you think about it, like usually there is people talk about a trade-off. So there is a trade-off between security and user friendliness and so on. But here there is no trade-off. Why is that? So our answer is that you just get more knowledge about the scene. So when you get more knowledge about something, you don't have to have a trade-off. You can just improve in all directions because there is less constraints, less restrictions that force you to have this trade-off, this was really nice. With deepfakes data, we got improvement around 1.62 times. It was not like such a huge improvement compared to physical test data, because there it is more complicated to catch the differences between different frames, and you really need to put you cannot just take like several frames and then average their embeddings. It's better like you should somehow really analyze the difference between different frames, so between neighboring frames and so on. So such a simple approach still gives improvement, but not as big as you would want to. And there is one famous data set in the world of face anti-spoofing. It's called MSU-MFSD. It consists of borderless spoofs. Borderless means that you cannot see the borders of the screen or of the printed paper. It looks like a normal selfie, but obviously with artifacts. Even you can see, I think, some reflections or some weird color distribution. So on this data set, we were able to achieve 0 false positive rate and 0 false negative rate, which is like the absolute performance of a classifier that machine learning engineers dream about. And in the night, yeah. So So that's what we got. And actually, when I looked for papers, that's a famous data set. When I looked for papers that like state that they have some good performance on this data set, I never saw 0, 0. Like, I mean, I saw only one weird paper by some Russians, and that was, I mean, they were connected to some startup, but this startup doesn't exist anymore. So I'm not sure if we can trust this archive paper, but other than that, I couldn't find any. So that's pretty nice. And again, it didn't require from us almost any efforts compared to what, I mean, we just built upon our baseline, which was already pretty strong. All right, a little bit of interactive session. So again, this guy, some of you raised their hands that this is a spoof attack. So let's have a look. Okay, so this photo is shown on the screen. I mean, obviously, there are frames that can help you to identify that this is a screen attack, right? But if you look just at this one single frame, it's really hard to identify. Okay, and this one got the majority. And let's see if you were right. Yeah, it's a deepfake. Yeah, very weird guy. So I mean, so the model was able to capture this weird behavior, but again, this is just this very simple implementation, and it can be much better. So once again, we tested. Today we showed you two experiments. One that combines RGB and depth, and another one that combines like RGB video. It was two separate experiments, and I think with that we see that there is actually no trade-off between security and user friendliness. If you use advanced AI, if you use appropriate data, you can keep the same passive experience for the user while increasing security a lot. And yeah, with video model you can see inconsistencies with time, and with the depth model you can drastically improve performance on 2D attacks. So yeah, that's the end of my talk. Thank you very much for your attention, and we are hiring.
Thank you very much. I think it was very interesting. So now let's have some questions from the audience. Do you guys have some questions? Yeah, go ahead.
Yeah, I've seen that you have added the language model embedding in the previous models, and I would like to know why you need the language embedding, or is it possible that you just use the end-to-end model without the language model? And what's the purpose of the language model there?
Yeah, that's a very good question. I mean, initially when we started working with vision language models, we thought, okay, what if we add some text information that describes the spoof attack? Like you can say, okay, this is a 2D attack. It's a replay. You can see a Moir effect and like some other description of this attack. What if it helps? So we did some experiments, and that doesn't seem to help. But when I talked about multimodal models, they are developed in the way to align in the language space. So we don't use this modality. We don't use like a language modality. But I mean, the model itself is developed in the way that everything, all the embeddings are aligned with the language embedding. So that's just how it works by design.
Thanks.
Hi, Luis Antonio here. Yes, I want to know if the video works like the 2D of the solutions. Like you have to train the model of the video with real image in real persons to cap to to count the deep fakes, you know, like how do you catch the deep fakes in the video, like if you do the same like strategy of the 2D.
Yeah, that's a good question. So maybe I need another talk about deepfake detection. I omitted that. Like I just said that we have some model for deepfake detection, but I never told you about that. So it's a classifier that we've been developing since last year, and yeah, that's a, like a dedicated model to work with deepfakes.
Okay.
And then we used this as a backbone for the video model. So we didn't need to train another video model because we used like the single frame or like single selfie model as a backbone. Does
Okay.
that answer your question?
Yes, and you use it the one that you train in the 2D in
Yeah.
the video one.
Yeah.
With the language embedding.
Yeah.
Thank you.
Like I think it's the classical baseline, right? You train your 2D model and then you use it frame by frame, and not perfect. You could do
Yeah.
better, you know, but at the same time, it's a very nice baseline. Yeah. More questions.
Yeah, but here the funny thing is that how to say, you can just run the model itself for each frame and then, for example, average the final scores or take maximum or whatever, some kind of ensemble. But this is much worse. This shows much worse results than if you run the backbone, you take the embeddings and then the same logic, but you build a classifier upon embeddings. So that's a very interesting finding. So yeah.
Hi there. Thank you. Thank you for the information. It was awesome. If I got you right, you teach the model to use the artificial intelligence, and firstly you said that you teach the model using only synthetic images to define the attacks, and afterwards you use some database of the original content photos to find the differences between them, or how it works.
Yeah, I think you're referring to this slide.
Yes.
Yeah, I mean that I was just describing depth anything v2. So it's a public model. It doesn't have anything to do with us particularly. I was just describing that there is like a teacher model that is trained on synthetic data, and then it helps like the student model with like kind of creating artificial depth maps for real images. But yeah, I mean this is just some public model. Yeah.
Okay, got it. Thanks.
No problem.
Hello. Yes, I just wanted to comment that we have been working on a similar topic on trying to predict depth estimation using specifically depth anything to another similar like out of the shelf pre-trained depth estimation models, and at least we haven't been successful at making it for purely synthetic data that is like what you described, like a flat image.
Yeah.
If there's no clue that this is like a photo or something like that, we didn't manage to make it work because, as you say, depth anything 2 is trained on like real world images.
True.
So yeah, just wanted to
That's
we tried that
interesting.
and we didn't manage to make it distinguish between real 3D
Yeah.
and 2D representation of a 3D.
So you had an opposite goal. You wanted to get depth for synthetic images, yeah?
Exactly.
Okay. I mean, I just saw some example when there was a drawing of Einstein, and it was able to predict depth like he was real.
Yeah,
But
because these kind of models, like they hallucinate
yeah.
the whatever they are trying to make.
And
So
what was your domain?
we do like 3D volumetric representation of things, like 3D capture, and that's why we were trying to research on how to predict, for example, how to create a nerve, a 3D representation from drawings that are not real 3D. So it's like perspective probably is not perfect and these kind of things. So these kind of models usually hallucinate some depth even from a flat drawing. They manage to create some depth.
Okay, so but this was not what you were looking for.
No, we were trying to, as you are doing, to try the model to understand that a drawing is not a 3D thing,
Okay.
even if it's a drawing.
So it's still hallucinated even when you tried.
If you use depth anything on a drawing of a building, it will predict the depth of the real building.
Okay, interesting. You can share your insights with me later. Okay.
I think it's more a feature than a bug, right? Yeah. More questions? Well, I do have one question, kind of generic question, I think. What do you think are the weak points of current solutions? So, where are the real problems in the market right now for this kind of spoofing and identity verification?
I think that deepfakes are rising really quickly, and they are. I mean, already now they are very hard to to be detected. And
I saw in your numbers that deepfakes are harder to detect than real attacks. Right?
Yeah.
It's kind of shocking.
Let me go back to this. Where was that? I think I missed it. Yeah. So indeed, like, human performance is not perfect. Like, they tend to reject also humans. I mean, so they are like, okay, I assume that in this data there are deepfakes, so I'll reject everything. So they rejected like 10% of humans, and even like if you take the majority, so it's really hard for so that's a really big thing, and that's why we invest heavily in deepfake detection, and that's why we try to like have as much information about what's happening as possible. Yeah, that's probably the biggest challenge.
Yeah. Thank you.
I was just curious how fast your algorithm.
It really depends. So are you are you referring to some of these models that I was describing? I mean, I know this model. It's very quick. It's like, I mean, 10 or 20 FPS. Yeah, this one, yeah. But if you use like many modalities, like if you use depth, if you use video and so on, it can get to slow performance, yeah. But still manageable, still real time, yeah. Which is also nice.
Yeah, my question is more of like curiosity. There's a company in San Francisco that is it's called WorldCoin. They basically scan the iris of like different humans, and they solve the same problem of like detecting deepfakes. I'm kind of curious, like, do you know about this company? Like, what do you see the future of? Do you see that like this kind of approach hitting some kind of deadlock where the deepfakes are just too good to be detected, and then you need this kind of iris scanning approach where you basically take like a hash of an eye, and that's like probably a bit more, like a bit more safe against attacks.
For me, it's really hard to comment on fingerprints or eyes scanning. I'm not like specialist in the field, but I know that there are also ways to attack these systems, to spoof them. Like, you can take somebody's fingerprint and use it. I mean, I don't know the techniques, but I know that it's possible, and probably with eyes it's also possible, at least based on Mission Impossible. So, but we as a related thing, we tried an experiment to detect deepfakes just based on crops of eyes. So we just looked only at the eyes, because as probably you know, there are more artifacts with eyes. Like, for example, light reflections are not corresponding. Usually, like, if you look in your, like, in the eyes of a person opposite to you, you'll see that two irises have the same reflection. So, for example, they have two lights or in both irises, or stuff like that, or there are different other artifacts. And we thought, okay, let's try to use this information and detect if it's a deepfake. And it worked. It worked pretty good, but it worked worse than the model that uses the whole face. So it just didn't bring any additional value. So just as a side note. But answering your question, I think, I mean, I am a believer in computer vision based techniques, and I think that we can still, like, if we go fast enough, we can find all these all these artifacts that any deepfake algorithm anyway produces, especially if it's a video, because consistency between frames is really hard, physics is really hard. So yeah, I think that's the answer. Yeah.
Thank you.
Just but at the end of the day, if let's say we reach a point where deepfakes are too good, let's say, it's possible as well that we just discard this way of identification. That's also, it's a bit the trade-off we have also, that perhaps at some point we'll say, okay, it's not a good way of identifying someone.
Yeah, maybe, but for now we are faster than deepfakes, because you see that's our version 5 and that's our version 6. So we are faster than them, and I hope that we will keep being faster than deepfakes creation models. Yeah, I think, and also, like, I mean, if you have a passport, and like, what's the alternative? How do you want to remotely verify yourself? You have a passport with a photo, right? So it's kind of based on your photo. Like, what are alternatives to that if you want to do it remotely? Yeah, sure. Yeah, true.
Also, one question regarding these two axes that you have shown, Efim. One of them was video. So have you tried the new model from OpenAI Sora that was released this week? Because it looks like pretty realistic thing in terms of face simulation and, you know, light consistency and so on.
Not yet, but it's interesting to try.
Let me know. Once
Okay, I will.
All right. So if there is no more questions, I think we are in the end of the talk. Thank you very much, Efim. Right now, we used to have here a part with networking, but for this time, we are going to move to the bar that is just here in the corner. There we will have a drink all together, so you can order a drink, and yeah, you're pretty welcome to join. Thank you very much. Thanks, Efim.
Thank you, everyone.